We have recently discussed the potential energy associated with gravitational interactions within multiparticle systems. Today we're going to discuss the potential energy associated with another fundamental interaction, electric forces, described by Coulomb's law. Let's start by reminding ourselves that in Coulomb's law, when we have two charged objects, say charge 1 and charge 2, then we know the electric force on charge 2 by charge 1 is proportional to the product of the charges and inversely proportional to the square of the distance, where the distance is the magnitude of the relative position vector r. Here the vector r locates charge 2 with respect to charge 1. We also recall that the direction of the electric force depends on the sign of the product of the charges. If the charges are of opposite sign, then the interaction is attractive. If the charges are of the same sign, the interaction is repulsive. Regardless, the electric forces are reciprocal, so that we know there is a corresponding electric force on 1 by 2, which is equal in magnitude and oppositely pointed. And so we can express this by writing the electric force on 1 by 2 is just minus the electric force on 2 by 1. Now to find the electric potential energy, U sub E, we can follow essentially the same steps we took before to find the gravitational potential energy. First, we find the entire work done on both charges within the system by the electric interaction. We then apply reciprocity and re-express the displacements in terms of the change in the relative position vector, delta r, like this. Then we can use our definition of the change in potential energy as the negative of this work, and here again, like in the gravitational case, we find that we only care about changes along directions radially toward or away from the relative origin, which here is the location of charge 1. So this is our result for small displacements. To find the change in electric potential energy for large displacements, we would have to break up the path into segments, where we could compute the change in potential energy on each segment using this expression, and then add everything up, meaning we would need to integrate in the limit of small displacements, where the integration is only along the radial direction. Again, we can think of the magnitude r as the coordinate along the radial direction, and the differential dr describes changes to this coordinate. dr is positive if r increases, and that happens if relative motion causes charge 2 to move further away from charge 1. So let's do this integral, and we end up with this result, which when we evaluate between the limits, we get this final result. By comparison with the definition of the change in electric potential energy as the final electric potential energy minus the initial, we find that U sub E, the electric potential energy associated with Coulomb's law, is this. Let's apply our knowledge of energy graphs to gain some understanding of how to use electric potential energy in the context of the energy principle. First, consider the case where we have opposite charges. For concreteness, say a proton and an electron. Here, clearly, the electric interaction is attractive. First, let's see if we can sketch the plot of the electric potential energy in this case. Give this a try. Here's the correct sketch. Notice that because the charges are of opposite sign, the product Q1, Q2 is negative, and therefore so too the electric potential energy. This looks very much like the sketch for the gravitational potential energy, which makes sense since that was also an attractive interaction. Note, just as in the gravity case, we have the general property that when the separation between the electron and the proton becomes large, the electric potential energy approaches zero. And as the separation decreases, the electric potential energy also decreases, meaning we would have a loss of electric potential energy that could show up, for example, as an increase in kinetic energy. This makes sense for an attractive interaction. Notice too that we can also sketch other energies on the energy graph. We can plot, say, the total energy E. If there are no external interactions acting on the system of the electron and the proton, then E is constant. Again, like the gravitational case, we can consider what happens when the total energy E is negative, or positive, or zero. With the total energy negative, we have a bound state, meaning the separation between the electron and the proton has a maximum value. We can think of this as the typical situation in an atom, where the electron is bound to the nucleus, here a single proton in a hydrogen atom, but this is true more generally for other atoms, where electrons are bound to the positively charged nucleus of the atom. We would expect the electron could escape from the positive charge if the total energy is positive. This would be the case of unbound motion, like we discussed earlier for gravity. For the total energy positive, the electron would always have kinetic energy at any separation distance, and so could escape the positively charged nucleus. Finally, as before, for the total energy E equals 0, we still have unbound motion for the electron. The total energy E equals 0 is the minimum total energy for unbound motion. Interestingly, there is a frequently encountered case where we start with E negative. The electron is bound, and then energy is added externally so that the electron becomes unbound. If the system is an atom, then we say that the atom has been ionized. Clearly, there needs to be energy transfer from the surroundings, and the minimum energy that needs to be added is that amount of energy that is just enough to raise the total energy to 0. In this case, this change in energy is called the ionization energy. Now, for completeness, we also need to consider the case where the electric interaction is repulsive, say, where the charges have like sign. So, for concreteness, let's consider the case where the charges are both protons. What would the electric potential energy look like? Give this a try. Here's the correct sketch. Notice that the electric potential energy is positive everywhere because Q1 times Q2 is positive. This potential energy again has the general property that when the charges are weakly interacting, here by having large separation, the potential energy approaches 0. That's just like the attractive case. What's new here is that as the separation distance decreases, the potential energy increases. Let's look at the full energy graph, including both the total energy and the kinetic energy. Notice we can only have the total energy E greater than 0, that is, total energy E positive, for any finite separation, because the electric potential energy is always positive for like sign charges, and kinetic energy can never be negative. This means if the particles are getting closer together, the electric potential must increase, and then the kinetic energy of the system must decrease. For any finite total energy, this means there will be a distance of closest approach where all the energy, E, is potential. And at that point, at that closest approach, the kinetic energy of the system is 0. The charges are not moving at this distance and so can't move any closer together. So in sum, we see that we can learn quite a bit about how this new potential energy, the electric potential energy, is used when we apply the energy principle to understand motion involving charges. And in all this, using energy graphs helps. We will have the occasion to use energy graphs for other potential energies in the future. For now, let's try one more clicker question that involves energy graphs with the electric potential energy. Let's consider each of these graphs in turn. Here we're dealing with a repulsive interaction, so the electric potential energy cannot look like this because this sketch is for an attractive interaction. This sketch is just plain wrong because it has a negative kinetic energy shown. This is unphysical. This graph is a little trickier. The electric potential energy looks right, and the kinetic energy is positive, but the sum, the kinetic plus potential energies, don't add up to give us the total energy. So this is wrong. The correct graph is this one. The electric potential energy is correct, positive for a repulsive interaction, and the total kinetic energy is correctly shown as the total energy minus the electric potential energy.